Hello. Hey Ryan. How are you today? That's good. That's good. I heard your first midterm is coming up next Wednesday, exactly 1 week from today, the 21st. Oh, yeah, the lab stuff. Let me send you my pre and post labs questions from when I had it. There's some questions that I reused, some questions that are new. What email do you want me to send it to? Let's see. Okay. I'm gonna use my computer. My MacBook is like so slow right now. Okay, I'm gonna send you the stuff here. Mm, one, managing B, so tabs here. Okay. Oh yeah, let me also send it to you, Amrita, the pre and post labs, and Ding as well. Let's see.
Oh, thank you.
Uh-huh. Yeah, no problem. Wait, what was the email again? Let's see. Here. Okay, 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 there it is. Send. Okay, I just sent you guys the pre and post labs. They're like for my quarter when I took it, they reused some of the questions, but some of them are new. I'll ask one of my tutees that have the new ones because I didn't have lab flow when I took the lab. Um, and then I'll ask them for the updated ones, and then I could like if I could share that with you guys as well for the team post lab questions. Yeah, but most of the questions should be reused. Okay. Oh, you guys aren't using lab flow? Is it PDF for you guys? The pre and post labs?
Yeah, it's on the PDF. Not,
Oh, what the heck?
yeah.
Did it change it back?
Yeah.
Wait, what the heck? If it's PDF, they might reuse the same kind of questions maybe.
Yeah.
Okay, let's see. Okay. So let's go over the synthesis problems that you sent me and the um predicted product question. Let me go back one to see those questions again. Okay, let's see. Okay. Mm, Lagging. It is lagging. Let's see. Okay, there we go. Okay. So the first synthesis problem that you sent me is this halo alkane converting into this product here? When is the problem set due for you guys?
It's due Friday night.
Friday night. Okay. I see. I don't have the answer key for these problem sets for B, but I do have the answer key for A and C for leave-ins. But I'm trying to get the answer key for B this summer session. So it's good that I'm going through with this with you guys now. Right. So we see here for synthesis, I like to figure out what's the similarities between the reactant molecule and the product molecule, right? Where we could say that this 1, 2, 3, 4, 5, 6 carbon chain is going to be this 1, 2, 3, 4, 5, 6 carbon chain right here, right? And then I say what's the differences. The methyl group on carbon 4, I'm going to say that it's that methyl group right there, right? The bromine is no longer there in the material, starting material. And in the product, we have an alcohol and an OR group that are adjacent to each other, vicinal to each other. Right. When you see this like kind of relationship, like an OH and an OR vicinal to each other, what functional group do you think that came from? Right. This is a 118A thing for especially for leave-ins class. Like she stressed this out a lot. Right. When you see an OH and an OR next to each other, what functional group do you think it was between 4 and 5? It's okay if you guys forgot as well, because I can go over that reaction again. But this is a 118A reaction. Right.
Is it epoxide?
Yeah, epoxide. Right. Did you remember that from when I went over them in the content review sessions back in winter quarter?
Yeah.
Yeah, that's good. Yeah, were you there in person for the sessions, or did you just review the notes, my notes?
I think I had the note.
Okay, that's good. Right. In 118A, I didn't record the sessions, but in spring quarter when I did the 118B review sessions, I recorded the session. So but Pascal is different than Nisiri and
No,
Levin.
I think you used to come to the AATC.
Oh, you used to go to the drop-in hours, the drop-in.
Yeah.
Okay, see. Did I help you? I don't remember.
Yeah.
Okay, I did. Okay, that's good. Did you go with the group or did you go like by yourself?
I went with a group.
I see. Right. So you're right. This OR and OH adjacent to each other are gonna come from an epoxide between 4 and 5. Right. So let's go backwards and do this. Right. And let's say, okay, right. If this comes from an epoxide, right, the OR is the one that's attacking the epoxide and breaking it open to the side right here, right? This oxygen of the alcohol here is the oxygen of the epoxide, right? Because ignore the OR and OH right now. The epoxide was that in the intermediate, right? Where it was wedged. Because when the OR comes, let's say methanol, CH3OH comes to attack, or it doesn't have to be methanol, because we'll see what it is, right? And it kicks up the epoxide on the other side. The wedge here stays as a wedge, but it would invert stereochemistry here, right? So this wedge would convert to a dash. That's why this OR here is a dash. It inverts the stereochemistry, right? So I'm gonna draw in the epoxide intermediate before it made that product right there. And then the methyl here is forced to become a dash, like that. So we see that the OR attacked the less subside of the epoxide. And do you remember what conditions would attack the less subside of the epoxide? Would it be acidic conditions or basic conditions? Yeah, basic conditions, that's right. And in basic conditions, it's going to be negatively charged, right? Everything is going to be either negatively charged or neutral charge. So we don't want to use methanol, CH3OH, and acid, H2SO4, because that's acidic conditions. That would attack the more subside. When you see your ORs on the more subside, then you would use the acidic conditions. But because the OR is on the less subside, we're going to use basic conditions where we could use CH3OK or CH3ONA. It doesn't matter what spectrator ion you use. K or Na is always positively charged, making whatever is attached to it always negatively charged, right? And that's the thing that we're looking for, the negatively charged oxygen, which is in basic conditions. And then the solvent is the neutral version of that, methanol, right? But this methanol is not going to react because the O minus here of the methoxide is stronger than the neutral charge on the oxygen, right? So this is in basic conditions where it would attack the less subside. Kick that up there. And we could do, let's say, acid workup, H3O plus, because when this O minus here attacks that less subcarbon and pops the epoxide up, break it open, the O minus would get protonated by an acid workup step. But make sure to separate them into separate steps, first step and second step, right? Because if you don't separate them and you put them together, this O minus here is actually going to get protonated by the acid that you put in, right? So they have to be step by step. You put in the base first to react with the epoxide. You wait some time after it like reacts, everything reacts, and then at the end you clean up the reaction by putting in some acid to protonate the O minus to become OH, right? So now this is gonna be a 118B reaction now. Let's say this is 4 and 5, carbons 4 and 5. Since we were in the alkene chapter, right? Let's say that epoxide came from an alkene like that, right? Alkene between but this was also, I think, included in 118A as well. That forces this methyl group that was dashed to become planar because that's now an sp2 flat and planar carbon, right? What reagent do you guys remember or know that would convert an alkene into an epoxide? Yep, MCPBA, peroxy acid. MCPBA would convert this alkene into an epoxide right there, right? But now, okay, so now from here to here is a 118A thing. Like we're gonna try to crawl our way into this double bond right here. To do that, right? Since we have a good leaving group, bromine here, we could use any kind of base. It doesn't matter if it's bulky or small, right? Because there's only one alpha hydrogen to deprotonate. So let's use NaOH and water, any kind of strong base. But her problem set, I think she restricts you because she gives you a list of things. But this would work as well. The general principles would apply. We'll see her answer choices after we do all the synthesis problems and the predicted products. Right. Let's see. Which would create this kind of double bond right here. Right. Now, let's go backwards here. Right. Let's go down. Boom. 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 MCPBA. Okay. So we see here the difference between this molecule and this molecule is the location of the alkene, right? But the similarity is going to be this carbon right here, carbon number 5, right? Because that carbon number 5 is double bonded for both molecules. So let's say that carbon had the good leaving group, bromine. What is one reagent we could use to put a bromine on that carbon right there? To put a good leaving group on this carbon right here. Oh wait, actually, it's gonna do something else. Well, let's say the leaving group could be here or here. Right. How can we add a good leaving group to the more subside at this alkene here? Right. Like how can we add a bromine onto this molecule? A good leaving group at the Markovna composition, the more subside. Right, HBr, right? But would the HBr go at that carbon or some other carbon? Yeah, we're gonna climb to the internal side of the molecule to get the more sub alkene, right? But if we put HBr to this alkene right here, is this the product we get, or is the bromine placed somewhere else? Yes, it's gonna be placed at this more subside right here because when I go over the mechanism here, let's say, boom, 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 boom. HBr, right? HBr is a strong acid. You can think of a base as a strong base because when we do resonance on an alkene, let's say I'll give you some kind of general alkene right here. The negative charge can be on either carbon. It could be on the carbon on the right side, or it could be on the negative charge could be on the carbon on the left side, like that, right? And we see that the other side has a positive charge, right? And are you guys familiar with carbocation stability? Like the more substituted the carbocation is, the more stable it's going to be, like primary, secondary, tertiary carbocation, right? In this case right here, we want the carbocation to be at this position because it's more stable, more substituted than this position. If we want this carbon to have the carbocation, we want that carbon to lose a bond, right? Which means that this carbon right here on the right side is going to be the one that attacks the hydrogen, right? So you can think of it as like when we do resonance on this alkene, we're going to give this carbon here the negative charge and this carbon here the positive charge because that's why the positive charge is more stable. And this carbon that is negatively charged is going to be the one that's attacking the H from the HBr. That's the base that's going to get protonated by the strong acid, right? And then we're going to kick out the Br leaving group to get this carbocation intermediate here, right? And then whenever we have a carbocation intermediate, this is the common step that students tend to forget. You have to look out for carbocation rearrangement steps. So either a hydride shift or a methyl shift, right? That's the common step that students overlook, right? Hydride or methyl shift. If you have no hydrogens and you just have methyls or an alkyl group, then you go for the methyl or alkyl shift. But in this case right here, if you look adjacent to it, it could become a tertiary carbocation, which is more stable than what it is right now, a secondary carbocation, right? But you never want to draw the arrow like this. If this is a mechanism problem, you never want to draw the positive charge moving to that more subposition. We want to explicitly draw out the hydrogen and then shift the whole bond with the hydrogen onto that carbocation right there. That's the whole hydride shift. We're shifting this whole hydrogen with its bond to that carbon right there with the positive charge that's missing a bond, right? And now this carbon is going to be neutral because it gained a bond, but this carbon here that just lost a bond is now positively charged, right? And that's able to happen because we are forming a more stable carbocation, a more substituted carbocation, right? And then the Br minus that got kicked out originally is going to come back as a nucleophile to attack that electrophilic carbocation to form this final product here. This halo alkane. Whoa, what's going on here? Boom, boom, boom. That. Right. So it's not going to be this. It's going to be this. Right. And then for this last reaction here, we're just going to do an E2 reaction. Okay, this is tricky now because when we do an E2 reaction, notice how both alpha hydrogens are equally substituted. So we could form a double bond either here or here, right? But we want the double bond here at the right side. And this is asymmetrical, so they're not the same thing because at the right side is an ethyl group, the left side is a propyl group. And we want it at the right side because we want the epoxide at the right side explicitly for this product, right? So we have to do something else here, right? If we don't want the bromine here, because when we do E2, we could get either this double bond or this double bond. There is a reaction that avoids carbocation rearrangement that is still Markovnikov. Do you guys know that reaction that is Markovnikov addition but avoids carbocation rearrangement? It won't add a bromine. It would add something else though. But it is a Markovnikov reaction of alkene that does not do carbocation intermediates. Oxymercuration, demercuration, right? Nice. Right. Oxymercuration, demercuration. And the reagents are Hg, OAC2, THF. Second step is NaBH4, and something, I forgot. Alright. But it's a reducing agent. Let's see, I don't know, THF. Let me just make sure what the reagents are. Hydroboration. No, not oxyhydration. Oxymercuration, demercuration. Oxymercuration, demercuration. Yeah. Okay. Yeah, it is mercury, OAC, water, NaBH4, and NaOH. Water. Yeah, other stuff. Right. um, and that would attach what group, what functional group at the more subside at this carbon here? Not a bromine, but an alcohol, right? And what reaction do you know that would make an alkene from an alcohol? E1 like reaction. So more specifically, dehydration, right? Dehydration reaction, dehydration of alcohol to alkene. We want to use H2SO4 and some high temperature that Levens put, probably like 135 degrees Celsius, 180 degrees Celsius, some high temperature. I have to check her lecture notes to see what she wants because each professor requires a different temperature, right? And that's using this table right here. Like depending on what alcohol you have. I'm going to simplify this, right, to primary, secondary, and tertiary only. I'm not going to do methyl primary unhindered, primary hindered, because I think that's more of a 1-in-A thing where she tests you on the very specific kind of substrates. But I'm going to simplify this to primary, secondary, tertiary. And then you react this with H2SO4. And then depending on if you have, let's say, low temperature or high temperature, these are the kind of reactions you're going to get. Hmm. And then let's do this. And then let's do this. SN2 like, E2 like, SN1 like, E1 like, right? Where in this type of alcohol right here, we have a secondary alcohol because the carbon directly attached to the alcohol is bonded to two other carbons, secondary alcohol, right? And we're reacting with high temperature, so we're going to do an E1 like dehydration reaction, right? Where the mechanism is to protonate this bad leaving group OH into a good leaving group OH2 plus, where that good leaving group OH2 plus is just going to leave by itself to form a carbocation intermediate. And then at this carbocation intermediate right here, I just realized something. Like it could do a carbocation shift right here, right? Which would end up at the problematic carbocation we want. Because whenever we go back to form the double bond, it has two equally substituted hydrogens to deprotonate to make the double bond, right? So that's also a problem. So we don't want to do dehydration because dehydration has a chance of carbocation shifts as well, right? There is a way though to convert the alcohol into a good leaving group, let's say bromine. Do you guys remember the reagent from 118A that converts an alcohol, or Katia as well learned this, like this summary class as well, into let's say a bromine or chlorine, doesn't matter. It's one of the weird letters, right? that was a problem because we ended up at that problematic carbocation that could make a double bond on either side, but we only want the alkene on this side here specifically to get this in high yield, right? But what is the reagent, the weird reagent with random letters that would convert this alcohol into some kind of good leaving group? It could be bromine or chlorine. It has a phosphorus on it.
Is it PBr3?
Yeah, PBr3, right? And that's just gonna convert the alcohol directly into a bromine. If you wanted to convert it into a chlorine, then you would use SlCO2. SlCO2 would convert the alcohol into chlorine, right? And then from here, we want to make the double bond at the more subside. So we want to use a small base. We don't want to use a bulky base because we don't want the alkene at the less subside. That's going to go backwards. So we could use NaOH, water. Strong base, strong nucleophile, that's small, like NaOH or NaOCH3, C, something like that, right? And then once we have this alkene that can only go to this position, not this position because that's too far away from the leaving group, then we do MCPBA to convert the alkene into the epoxide. And then from the epoxide, we do the epoxide opening in basic conditions with this specific OR group that we want in the product, right? So this synthesis problem, I used 1, 2, 3, 4, 5, 6 reactions, right? But I don't know what the problem set like questions are, but this is how I would do it on the test. We'll go over well, actually, I'll go over the problem set options and then see and try to match it up with this thing here and then send you guys a text message, Amrita and Ryan, before you guys submit it in the Canvas or something. But does this synthesis make sense, like the process of this? Yeah, okay. That's good. That's good. Right. Notice how at the beginning, right, I used reactions that had a carbocation intermediate, which was susceptible, vulnerable to a carbocation rearrangement, like a hydrogen shift or methyl shift. And that was problematic because when we have a carbocation at that most substituted carbon there, the double bond could either be here or here because it's asymmetrical, right? Which could still give us this product here, but in low yield. There's going to be a mixture of that product and this product as well, right? But if we don't want that product and we only want this product, then we have to avoid carbocation rearrangement using oxymercuration, demercuration, and PBr3. Right? We can't use dehydration. We can't use HBr because those reactions involve carbocation rearrangements. So when you guys study for the next exam, I think you guys have a note card, right, for Leavens class, like a 3x5 flashcard. Okay, yeah, that's good. That's good. You can just write all the mechanisms, which ones has a carbocation rearrangement, and avoid those if the synthesis requires that. Yeah. Thing. Okay. So that was the first synthesis. Let's go over the second one. Let's see what it was. It is going to be this one here. This halo alkane, that is cyclohaloalkane. Boom. Starting material reagent. Gonna be this right here. Are you guys familiar with the reactions? Like, did you guys learn all of the alkene reactions yet?
Yeah, she finished them today.
Oh, you finished them today, so yeah, that's not much time to like absorb the material because it's still fresh in the mind, right? But I'll guide you guys through the reactions of what you guys need to know for these synthesis problems. We see here that in the reactant molecule and the product molecule, we have a cyclohexane with the methyl group sticking out, right? That's the thing that's staying still, the similarities between these molecules, right? The difference is there's no more good leaving group, and we have two alcohols that are vicinal to each other or adjacent to each other. And we see that they are syn to each other as well, or cis to each other, which means that a syn addition reaction happened here. What reaction? Wait, actually first, what functional group do you guys think that these alcohols came from? Right. Let's say like what was between these two carbons here? What functional group was between those two carbons that gave these two adjacent alcohols that are syn to each other? Right. What did this come from? This product molecule. What reaction would do you know that would convert something into a vicinal syndiol, like two alcohols that are adjacent to each other on the same side? Right. Yeah, yeah, we did this yesterday, right? Let's say that these carbons here holding the alcohol, it came from an alkene, right? Wait, alkene right there. The osmium tetroxide reaction. Osmium tetroxide reaction with an alkene would give rise to two alcohols adjacent to each other on the same side, syn addition. OSO4, second step, some kind of random thing like NaHSO3, I think, and something like that. It's two steps though. Osmium tetroxide and second step, some kind of reducing agent like that. That would give two alcohols, one on each carbon of the on the same side, syn addition, either dash or wedge. Right. Okay, now this is a 118A thing. How can we care? Right? How can we crawl from this good leaving group to make this less stable alkene? Can you guys hear me still? Am I cutting out?
A little, yeah.
Oh shoot. What about now? Hello, hello.
It's been fine. It's just been like a couple words here and there. I just
Oh,
thought
I
it was
see, I
me
see.
because mine was yesterday.
Yeah. No. Because Zoom just told me my internet connection is unstable, and I was like, oh shoot. Can you guys hear me? Right. Wait, actually, no. There's some 118B reactions here that we got. Yeah. Yeah, we want a double bond right here. Yeah, so there's a 118B reaction here. It's just not all 118A. Yeah, so we gotta climb again, but this time we're climbing in the less stable position. climb throughout the molecule. A lot of climbing in this alkene chapter, climbing through the molecule. Right. Where what reactions do you guys know that can synthesize alkenes, can form alkenes? What kind of reactions form alkenes? Well, this is a 118A. What reactions form alkenes?
E1 and E2.
Yeah, E1 and E2, right. And let's say that this came from an E2 reaction where the leaving group is going to be on that carbon right there, right? Because that carbon right there, we see that that could have came from that alkene, right? Like let's say the leaving group was right there on that carbon. Because we see that the alkene that was formed is at the less stable position, not the more stable position, what kind of base do we want to use here? Do we want to use a small base or a bulky base?
Bulky.
Bulky base, right? And what are one of the two bases that you know that are bulky that you could use for Hoffman E2? Right, tert butoxide or LDA. Uh-huh. LDA or tert butoxide. Right. In leavens, you might see it as in this form, CH3, 3, COK. and its solvent 3CONA, or and its solvent as well, like the H version, right? Okay, so I'm just gonna do Zaitsev E2 using a small strong base strong nucleophile to make the more sub alkene right here, right? But we see that the leaving group is on the less subcarbon instead of the more subcarbon. So call that the anti-Markov-Markov position, the less subcarbon. What reaction do you guys know that adds a functional group at the anti-Markov-Markov position, the less sub position? But think of it as the opposite of oxymercuration, demercuration. There is a reaction that adds something to the less subcarbon. Hydroboration oxidation, right? Hydroboration oxidation, which is BH3, something. The second step, hydrogen peroxide. That's the point for the second step. NaOH, water. Right, and that's gonna add alcohol to the less subcarbon of the alkene, like that. And then we went over this already to convert alcohol to some kind of good leaving group, PBr3 or SlCO2. And then from this we could use Hoffman elimination using a bulky base like LDA or tetrodoxide to form the less stable alkene. And then from that less stable alkene, we use osmium tetroxide reaction to form the vicinal syn-diol. Vicinal meaning that the two groups here are adjacent to each other. Syn meaning that the two groups are on the same side, cis to each other. And diol meaning two alcohols. Di, two, ol, alcohol, two alcohols. Vicinal syn-diol. Right, that's the osmium tetroxide reaction from an alkene. Vicinal syn-diol. Okay, so this one had 1, 2, 3, 4, 5 reactions. Okay. Next one.
Wait, I have a quick question.
Yeah.
So for the last step, what's that reaction called?
This reaction here, let's see.
OSO4.
OSO4, right. Vicinal syn-diol formation or something. I think it's a specific name for it. Like it's not that clear. Let me check my notes for that for you really quick. Right. It's not as good as like oxymercuration, demercuration, or hydroboration oxidation. There could be multiple names for it as well, like addition of HX to alkene or addition of nucleophilic acid to alkene. Yeah, let me double check that with you. Yeah, that's good that you're asking like what's the reaction name called, because whenever you do these predicted product mechanism and synthesis problems, label each reaction name and draw out the mechanism if you're required to know it for each, and explain to yourself why each arrow is happening the way it is. Well, actually, no, you get no card, so you don't actually need to do that. But for Leibniz, I forgot Leibniz usually has a no card. Let's see, 118. 118B. Let's look at my notes. Okay. OSO4, osmium tetroxide. No, that's oxygenation, hydrogen, NBS, carbene, peroxy acid, HMCPBA, vicinal diol synthesis. Okay. I have it as vicinal diol synthesis from alkene. There might be some other name to it, but to describe the reaction, it synthesizes a vicinal diol, or you could specifically say vicinal syn-diol synthesis. So there's no clear name for that reaction. Oh, Stevens calls it osmylation. Osmylation. That's my first time seeing that term, osmolation. Osmolation. Oh yeah. Ever looked up osmolation? It's that same reaction. Okay, that's good to know. Osmolation. Osmolation. Nice. Yeah. First one was Zaitsev E2. Second one was hydroboration oxidation. Third one, I don't know this one. OH2Br. This one, Hoffman E2. And then the last one, osmolation. Osmolation. Okay. Let's do this one. 7-numbered ring. This boom. 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. Oh, that's a 6-numbered ring. Wait, what the heck? 1, 2, 3. One, two, three, four, five, six, 7. Okay. Reactant. We want to create. I'm just gonna copy and paste this. We want to create this product. And then I'm going to draw out the CH2, CH3 in bond line form like that. Right. We see here that there is an OR group. And then usually the alcohol is adjacent to it like that, meaning that these two groups came from an epoxide, right? So let's go backwards and say that this came from like OH right there. Wait, let's think about this. Let's think about this. Right. Imagine the OH wasn't here before. And then the OH was right here, which means that these two groups, the OR and OH, came from the epoxide. And the epoxide was something like this, right? Between those two carbons. If the OH was here, let's say that OH became a good leaving group, Br, right? And then that good leaving group could do a Hoffman E2 reaction using LDA or terbutaoxide to make an alkene right there, the less subalkene. And then we see here the alcohol is attached to the less subcarbon of the alkene. And whenever we see a less subcarbon of the alkene, we think of anti-Markovnikov addition, which is hydroboration oxidation, right? Which is going to create this alcohol at the less subcarbon right there. So when we go backwards here, let's say that hydroboration oxidation happened in the last step. Okay. BH3, GHF, second step, hydrogen peroxide, NaOH, water. Right. My thought process was this. I see OR. I predict or expect there to be an OH right there to show that that came from an epoxide, but there was no OH there. The OH is on here. Right. And I was like, how did the OH crawl over here? Right. And I see here that the OH is at the less subcarbon. And when I see a less subcarbon, I think of anti-Markovnikov reaction. And when I think of anti-Markovnikov reaction, I think of this hydroboration oxidation reaction that came from that double bond. Right. And then I think to myself, how can I create that double bond right there when there was an OH here? So that I could convert that OH into a good leaving group like bromine and then do Hoffman E2 using LDA or terbutaoxide to create that Hoffman E2 product, right? Let's say that we went backwards and used LDA to form this intermediate using this substrate here, right? And then we said that that substrate came from an alcohol reacting with PBr3, which converts the alcohol into bromine, right? For this problem set, I don't know if Leibniz wants us to do it this way because there's like multiple routes for these synthesis columns, but I'll double check for you guys what she wants and what she's asking for, what she puts in the list. Right. OH, and then we see OHOR. That could come from an epoxide. Let's draw the epoxide. No stereochemistry, so we don't have to worry about the wedge or dash here. Epoxide. And in this case, it doesn't matter if you do it in acidic or basic conditions because both of the carbons of the epoxide are equally substituted. Right. So let's just use acidic conditions. Ethanol and H2SO4. Okay. And then we know that that epoxide can come from an alkene, which is going to be this alkene. Right. And then how can we create this alkene from this alkene? What are the two steps that are required for that transformation from this alkene to this alkene? Right. These synthesis rounds are kind of long. Yeah, HBr, that elimination, because we see here from this less stable alkene, if we want to make an alkene right next to it, then we gotta put a good leaving group right here, right? Which to do that, we could use HBr, which would put the Br at the more sub position. And this would have a carbocation intermediate, but when we do this reaction here, the carbocation is already going to be at its more stable position in the intermediate, right? That tertiary carbon, where the bromine is going to attach to, right? So we don't have to worry about hydride or methyl shift here. Bromine is going to be here. And then we want to make the most stable, more substituted alkene. So we want to use a Zaitsev E2 reaction. So we could use any small, strong base, like NaOH or water. On Levin's problem set, she could include like NaOCH2CH3, like this NaOCH2CH3, and its solvent, CH3CH2OH, which is still gonna be Zaitsev E2 because this is considered a small, strong base, strong nucleophile. Right. So in this synthesis, we did HX addition to alkene in the first reaction. We did Zaitsev E2. We did epoxidation. We did epoxide opening in acidic conditions, but it didn't matter in this case because both carbons of the epoxide are equally substituted. So you could have done basic conditions as well. We did OH2Br, and then we did Hoffman E2, and then the last thing, hydroabrasion oxidation. So for these synthesis problems, I like to think about the similarities between the reactant and ending material. What's the differences? And then go backwards, retrosynthesis. Think backwards of what you could do and go forwards as well. If you get stuck, go backwards and forwards and then try to meet in the middle and connect the two pieces for synthesis. Right. And this, there could be multiple correct answers as long as you get the correct answer in high yield and there's no other mixed products, no low yield mixed products. Right. So this one was 1, 2, 3. 4, 5, 6, 7. The longest one so far that we did. Any questions on this synthesis? Okay, let's go over the reaction that you sent me and its mechanism as well. So in the starting material, we have an alcohol. On the reagent, we have a strong non-nucleophilic acid, H2SO4, and alcohol as the solvent. Right? And this alcohol that you gave me is not specific. It is going to be broad and general because of the R group, right? The R group can represent an ethyl group to give it ethanol, an isopropyl group to give you isopropanol, but the R group is any hydrocarbon chain, right? Any hydrocarbon chain, carbons and hydrogens. ROH is an alcohol, right? So whenever you see a strong acid here, an acid-base reaction is going to happen. You're going to look for your most basic atom, which in this case, our most basic atom is the oxygen of the alcohol, right? The first step of the mechanism is to protonate the alcohol and kick out an HSO4 minus conjugate base. And that would give this oxygen an extra hydrogen. It's now OH2 with a positive charge because it has 3 bonds and 1 pair of electrons. Right? This step right here converted a bad leaving group, which is OH, into a good leaving group. Right? And then think of this as an SN1-like mechanism, where in SN1E1 reactions, the leaving group, if it's good, will just leave by itself. It will leave by itself. And then when it leaves by itself, we're going to have a positive charge on the carbon that lost the bond, a carbocation intermediate. And at this step here, we have to stop and look for any hydride or methyl shifts that are possible, right? We see that we can do a hydride shift because at the right side, the carbocation can be more stable, which is a tertiary carbocation, right? But we don't want to draw the carbocation moving there. Like never draw the arrow if this is a mechanism problem, right? Because positive charges never move. Only electrons move or bonds move towards the positive charge or the electrophile, right? So this is a hydride shift, which would convert the dash methyl into a flat planar methyl because this carbon is now sp2, flat and planar, right? And then from here, the ROH, whatever the R is going to attack that carbocation to get this intermediate here. Okay. You could star the oxygen to show that that's the nucleophile. You could dot this carbon to show that that's the electrophile. And we're going to make a new bond between the star and dot. That's the dot carbon right there. It's attached to a methyl group, which is that methyl group. And this is the new bond between the star and dot. The new bond between the nucleophile and electrophile. That oxygen there is that star right there, right? But that oxygen is attached to an R group and a hydrogen, right? And because this oxygen has 3 bonds, it's positively charged, right? Now the last step is to neutralize and deprotonate that oxygen with the HSO4 minus to reform our acid catalyst, to reform our catalyst in this reaction. Right? Grab that H, the bond between that H that's being grabbed and the oxygen is going to go onto that oxygen to make it neutral. And that's going to give us this OR right there, right? And then the H2SO4 acid catalyst that gets reformed. And whatever the R group is on the alcohol is going to be this R group there. So we just formed an ether here, ROR. Right. And I'm assuming this is in low temperature because there's no temperature given. But if this was in high temperature, then some other reactions can happen. E1 reaction is going to happen. Right? But I'm assuming this is low temperature, which is going to be an SN1 reaction, which is going to be relating to this chart right here, an alcohol with H2SO4. If your solvent was a water, right, instead of ROH, and if it was H2O, then H2O would attack, and your product would be OH instead of OR, right? Because if water attacks, then this will be the intermediate here, where the oxygen has two hydrogens. And to neutralize it, we have to take away one of the hydrogens. But when we take away one of the hydrogens, that oxygen still has one hydrogen, which is an alcohol. But in this case, we use an alcohol as the reagent, which means that when we take away one hydrogen, it's left with one R group. So it's an OR, not an OH. Right. Okay. Oh, that's perfect. Like all the questions you sent me, these two synthesis problems and the practice one, like took the almost a whole hour. Do you guys have any other questions or topics you guys want to go over? Did the mechanism and synthesis thought process make sense for you guys? That's good. That's good. Yeah, that's good. Okay, let me give you guys a practice problem to end off the office hour session. A synthesis problem with alkenes. What reactions do I want to include? Okay. And this is good for Katia too, because wait, no, Katia is like you're not being tested on alkenes, huh? You tested on alkynes, organohalides, and SN2, SN1E2.
Yeah, no, somehow we're past the alkenes
Alkene,
in
yeah,
the equivalent to 118A. Don't ask me how.
Okay. Okay, try the synthesis problem and let me know your guys' steps on this. Yeah. Look at the similarities, the differences, try going backwards, retrosynthesis, try going forwards, and try meeting in the middle. Right? And then look at the functional groups present, the relationship between those functional groups, and think about what reactions can create that, those functional groups and the relationship between those functional groups. Right? So those are some like things to think about when you guys are doing these synthesis problems. Okay. So let's think about the similarities here. We could say that this highlighted portion of the reactant molecule is going to be the exact same molecule as same part right here, right? Where we see the differences are that there's no more halogen on the product, and the product has two alcohols, right? And then we see that the two alcohols are adjacent to each other or vicinal to each other, right? Which means that between these carbons here, that could have been a alkene, right? That could have came from an alkene between those two carbons. And then what did we say earlier that would create a vicinal diol from an alkene? What we actually would put alcohols on both carbons of the alkene. Yeah, OSO4, osmium tetroxide. Second step, NaHSO3. And specifically, it would do a syn addition, but because this carbon here is not a chiral center, because it has two hydrogens, stereochemistry is not required here, right? We don't have to put a wedge or dash, and because it's not required there, this is the only chiral center, which this could represent either a wedge or a dash, right? That's why there's no stereochemistry, because that's not a chiral center, right? And now, how can we make an alkene here, right? At this position here, if our leaving group is all the way over here, how can we crawl all the way to this less sub position? What's the sequence of steps that we could do? Right. Well, yeah. Well, first, do we want to make an alkene here at the left side, or do we want to make an alkene here at the right side? Yep. We want to make an alkene at the right side, the less sub position, because that gets closer to the alkene we want. But the alkene on the right side is less substituted, which means it's a Hoffman E2 reaction. So we got to use some kind of bulky base like LDA or tributoxide, right? And now, what's the next step after we get this here? How can we create a good leaving group? There's a problem here. Because these two carbons here are equally substituted, but we want the leaving group to be here, but then it could have been here as well. So oopsie, let me do that. Boom, boom, boom. Yeah, those are problem there. Right, because that alkene had two carbons that are equally substituted. So when you try to put a good leaving group there, it could go the other way as well, right? Because it's equally substituted. So you can't, if you use oxymigration, demigration, or hydrogen oxidation, it could go on either carbon because they're both equally substituted, right? But now let's say that there was a methyl group there, methyl group, methyl group, methyl group. How can we put something at the anti-mark position? Oops. Oh yeah, HBr and ROR. That's the other thing I forgot about. HBr and ROR, and that would have just give you the bromine on the less sub carbon directly, right? And then we could do LDA again to do Hoffman E2 to put the alkene at the less sub carbon, right? So what we did was Hoffman E2, HBr war, which was radical HBr radical HX addition. No, it has to be HBr specifically. It can't work with Cl or other iodine. Radical HBr addition to alkene, and then we did E2 Hoffman, and then we did osmolation, right? And then think about that reaction on a problem set, right? It's most likely gonna go through from here to here. No, actually not. How about the second one here? PH3. Oh, yeah, this one right here, right? There's a shorter route to go from here to here, which is probably what the problem set did. And it's higher yield as well, right? From here to here, which is HBr roar. I forgot about the roar, the radical addition of HBr, the antimark position. Right? Instead of doing hydrogenation oxidation and then converting the alcohol to bromine with PBr3, we can go directly to the less sub Br using HBr and roar. Right. So that's probably gonna be the answer for the problem set, the HBr and roar. Yeah, nice one. Yeah. Right. And that reduces it. That reduces the steps, giving higher yield. Does this one have it? Let's see. Nope. Yep. Okay, nice. Yeah. Nice. Okay. Any last minute questions? Okay. I will see you guys. Yeah, no problem. Good luck on studying for the exam next week. And I'll see you guys maybe in the next office hours or the next scheduled private session. No problem. Yeah. See ya. Night. No problem. Okay, Katia. We're gonna move over to the next like the other one, and then we're gonna end the session at like 11 or 11:15 around that time.
Sounds
Because,
good.
I ended it a little bit late.
No worries. It's all good. I'm like,
Yeah.
okay.
See you there.
Okay, bye.
Wait, Jose. Roblox gang later. I have to stay up to study for exam.
How about it's past my bedtime?
You fix your sleep schedule?
And you have another tutoring session?
With her right now.